All right, so if you look at example 4 at the top of page 47, it says there are 3 special Maclaurin series you must know. What are they? For sure. Yeah. E to the x, cosines x, and sine x's. We've worked with all of those already. There's going to be one more added to that mix next week, and it's 1 over 1 minus x. So there's 4 you're going to have to know. This one, they didn't tell you what that's the expansion of, for example, 4, but what is it? You can recognize it. So it won't be a surprise to you that when they're asking you to find f prime, if we were to do that manually, what would I get? E to the x right back at me, right? So the series expansions and their function equivalents, they behave very much the same way. So their derivatives are the same, their integrals are the same, and all that. You can add them, you can subtract them, you can multiply them. Number 5, there's one in your note packet where you're going to need to integrate. It doesn't explicitly say in your homework packet to integrate, but it's going to give you h prime, and it's going to ask you for h. And you'll already have the expansion for h prime in a previous problem, and then it's going to say, well, what's h? So you're going to know that you're going to need to integrate your series. So if we just go up here manually, and I want to show you what happens with the integration. If you were to integrate your series, you're going to be integrating 1 plus x plus, so go ahead and write this down. We'll do example 5 here, because with the integration there is something old that we need to remember. So we're going to be integrating also our general term. Observer, didn't you say you never took calculus? So this is all going to be like me sitting in a French class, but it's good stuff anyway. Anyway, when we go integrate this term by term, take a look at what happens here. Antiderivative Brie of 1. If you get it wrong, you're voted off the island. Thank you. Antiderivative Mitch of x. X squared over 2. Antiderivative, you're off the island. X cubed over what? 3, and then it's over 2 factorial already. So, and again, I'm just integrating term by term, adding 1 to the exponent, dividing by that, but then when I do that, I end up getting a 4 factorial, plus dot, dot, dot. The general term will get affected in the exact same fashion. So you might be saying, why is she doing this example? It's way too easy. It's for the one little thing we need to remember about when you're integrating an indefinite integral. What do I need on there? What do I need? Carl, this just beeped in my ear that it's, I should have charged it. Sorry, now I'm going to be tied up front because I'm attached. Excuse me. I was going to behave today, but I'm not going to be able to. All right, so now I'm attached. This is how far I can move. All right, here we go. Sorry about that. So we need to have Carl on there, but this is the deal. This series goes on to infinity, so we can't really put Carl at the end of infinity. So when you're integrating with your series, where do you think I put Carl? In the front. Yeah, and so this is really going to be c plus x squared over 2 plus. So we're going to take Carl and put him at the front of our sum instead of at the end, and who matters because addition's commutative and it doesn't really matter. And then what do we have to always be given in order for you to figure out who Carl is? What do they have to give you? A point. And so they will. All right? And almost always they tell you what happens at the center. If you're not given a point, then you determine what happens at the center. What's the center of this Taylor series? Right. Had that been an x minus 2 squared, your center would be at 2, so they'd probably tell you what f of 2 is, or you would figure that out. Does that make sense? I believe there's one in your homework where you're going to go, well, what's the point? Not like, what's the point? Like, why am I doing this? But are you with it? You get what I mean? That was English. Right? I mean, like, what's the point on the graph? And you're going to figure out what happens at the center. So put that in the back of your brain. So if they tell me a 0 has to poop out a 1 in my function, right? Who's Carl? 1. Yeah, because all this will go to 0. So notice it shouldn't have shocked you that I'm getting the exact same function back because this is the series expansion for which series you need to have memorized? This is e to the x. You know the derivative of e to the x is e to the x. We also know from Calc 1 that the integral of e to the x is e to the x. You might say, well, what about this general term? Now it's x to the n plus 1 over n plus 1 factorial. It doesn't need to be. Again, you can just go right back to this, right? As long as you tell me where this is starting. Is this going to be at n equals 1 or at n equals 0? Yeah, this would be at n equals 0. All right, so know that other than that. So you can see why that one had to be a plus 1 because, you know what I mean? It works out nicely. So that example I hadn't done yet. We did this yesterday, right? And we talked about, did we do this one yesterday? All right, so we're going to do number 8 next. So we like it when they tell us it's a Maclaurin series for one that's just a little bit off of one we're supposed to know because we get to just manipulate it. There is one in your packet that bothers me, and it's weird because last year was my first year teaching Calc 2, obviously because it was the first year we had it. But I didn't catch it, and nobody in the, that's the same worksheet I gave last year, and we don't have a book, so I find things online, and this source is really good. But go to your packet. It's number, and see if you can tell me why. I was like, this one's kind of bugging me. And I am tied to my computer, so I want to, can you bring your packet up here? Sorry if you're listening to this video because you're absent. I have a cord and it's like I'm on a leash. All right, anyway. Puppy can't move. Up. All right, anyway. It's number 8, and you've already gotten that far, and you did it right. She's got a perfect general term for number 8, but there's something about number 8 that's really bugging me. Anyone want to anticipate what it is? It shouldn't be on there, and I didn't write this worksheet. I love it, though. This is one of my favorite sources go-to for your worksheets, but the person, I don't know if it's male or female, number 8's bothering me. Yeah, the first term of it, and Gabby, you have it right, is 1 over x. Why is that bothering me? Where's this centered? It's centered at 0. You know what I mean? And when we first did these, we said that it had to have an infinite amount of derivatives at the center. And that one actually, if you look at it, what does it have at the center? If you look at the original, I think it was cosine something x, it doesn't matter, over x. At the center, which is when x equals 0, what does the graph actually have? It has a, what? When you have a 0 in a denominator, not a whole. It has a vertical asymptote, and you can't even take a derivative. So that problem bugs me. If you already did it, I guess it's the process better, but that one had a structural problem. So you could skip it if you didn't do it yet, technically, but some of you did. This one won't have an issue, though, so let's take this one out. I want to do the Maclaurin series, which means I'm going to be centered at 0, which is nice. You might want to get used to writing those out. So I'm going to write g of x is going to be equal to g of what? 0 plus, but for this one, I wouldn't do that because this is the one you're supposed to have memorized. So let's go take a look. For cosine x, see if you've got it memorized. Go ahead and write it down. Cosine x. I'm not going to take it from the get-go, but you should know how to. We've done it a bunch, so cosine x's should be memorized. You should be debating whether it starts with a 1 or with an x. Ben, does it start with a 1 or an x? Why? Yeah, that's the easiest way. And is cosine an even or an odd function? It is. All right, so this is the one that goes like this, and we know that. So go ahead and write it. And I'm going to go plus dot, dot, dot. I am going to write the general term, okay? The general term, true or false, e to the 2n over 2n factorial. True or false? Jaden, you're shaking your head no. Why? I forgot the alternator. Okay, which is very important. So I'm going to put the alternator in. Our alternator is a -1. What power? N, perfect. Plus dot, 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 dot. All this wants me to do is x cosine x. So since I'm still maintaining that same center of 0, I'm just going to take and multiply every term through by an x. So that becomes x minus x cubed over 2 factorial. This is an easy one. X to the 5th over 4 factorial plus dot, dot, dot. Still needs the alternator. right? But now when I multiply this by x, I don't even need to look at these. I always like to mess with my general term. What's my exponent on x now? X to the 2n plus 1. Yeah, I'm going to have another one tacked onto there over 2n factorial. And that's super easy. But if you were asked to do its derivative, you could just take the derivative right here, or its integral. By the way, the power of series is huge historically because what it allowed people to do is integrate things that normally they couldn't. For example, this is not something you can traditionally find the integral of, because your go-to would be u sub. Who's u? Well, neither one works. You know what I mean? This, maybe you could try by parts for that. You know what I mean? That might have been worthy of a by parts actually, but this one isn't. And so it allowed them to integrate things that normally they couldn't, which was huge because it was a big deal. So next one up, this is actually a cool one. You won't think it's cool, but I think it's cool. So this says to find the Maclaurin series for H. H is really a variation on a theme by who? Really, which one am I just going to mess with? E's. All right, so let's go do that. That's one. You shouldn't take grassroots. You should write it down. Julia, you said it, so you're going to have to tell me what it is. Da da la la. General term. Da la 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 la. All right. So now what I'm going to do is I'm allowed to add, subtract, multiply, integrate, derive. I can do a whole bunch of stuff. I'm going to do e to the x's next. All right, so for e to the negative x, all I do is replace all these with a negative x. So let's go see what happens. I get that. Negative x squared is still positive, so I'm good to go. Negative x cubed is going to be negative, yada, yada, yada. Now what actually would be in my general term, though? An alternator. Score 1 for the team, x to the n over n factorial, right? By the way, could I write it as negative x to the n? What do you think? You can, but usually you pull your alternator out of your general term. Like if you're doing one on the homework and you're like, oh, I got a negative x over 2. Pull a negative 1 with an alternator out. It's the user-friendly version of it. Anyway, I forgot my dots. What are those dots called? They've got a name. Consult the World Wide Web. Somebody, I want to know. Do you know what those 3 dots are called? What are they called? How do all you know and I don't know? Oh, there you go, English. Just kidding. All right, yep, ellipses, thank you. Anyway, I had forgot them and I have too many. So take them off. Them ellipses, take them off. Right there. 3, I know. All right, anyway, I'm going to add these up. I'm nice and chill today. So now I'm going to add these up because I need my numerator. And I'm going to get e to the x plus e to the negative x. I'm just going to tally these up. Notice what's going to happen. Can you see it? All the odd powers have an alternator in the second one, so they're going to disappear. So I'm going to get 2x squared, right? X squared over 2 factorial. Then I'd get 2x to the 4ths over the 4 factorial because I'm going to be adding those up, right? And then I'm going to get 2x to the 6's over 6 factorial. I'm not going to cancel these. And by the way, get used to not. You like to see things still beefed up because my next step is to divide everything through by what? 2. And then what I'm going to get is a 1 plus x squared over 2 factorial. All these 2's that I just were created are going to disappear. I'm going to get x to the 4th over 4 factorial. What does this look an awful lot like? It looks like cosine in the absence of the alternator. Yeah, so its general term is cosines with the alternator obliterated. And this actually is the series expansion for something you haven't heard of yet. It's called hyperbolic cosine. Anyone heard of that? And we used to, when I was in higher levels of math, maybe we'll introduce it to you after the AP exam. It's not a hard concept, but we would call it cosh of x, and hyperbolic sine we'd call sinh of x, even though it's like that. But you know how cosine is on the unit circle, right? Cosine and sine deal with the standard form of a circle, and you give its cosine and its sine, we know all that, as points on the unit circle. Hyperbolic cosine and hyperbolic sine are on what's called the unit hyperbola, which is this. I'm just giving you some math trivia that you shouldn't write down. It's actually not trivia. It's pretty cool. Anyway, do you guys know what a hyperbola looks like versus a pair? There we go. Thank you. Bree looked all like distorted, but it goes like that. And actually it's over here, but we only work with the right lobe. But every point on the unit hyperbola, you would call it, its coordinates are called hyperbolic cosine, hyperbolic sine. And instead of the angle being right here, the angle is right here. And it's used a lot in high levels of physics. I think it has to do with sound and electricity and such things. You could consult the World Wide Web for that, which I like to do. By the way, here's something interesting. Are you ready? According to my calculations, hyperbolic cosine, that's what this is, you don't need to know that, is the average of e to the x and e to the negative x, right? According to this, I went and graphed on Wolfram hyperbolic cosine because I couldn't remember what it looked like because it's been 20 some years since I took a class that used it. So I had it plot hyperbolic cosine. And if I were to go graph e to the x, it looks like that. And if I graph e to the negative x, it looks like that. And doesn't it look like hyperbolic cosine is averaging them? Isn't that weird? Isn't math weird? Yeah, so it's about to get really weird right now. We did those yesterday? All right, last up, the creme de la creme. This is sometimes known as one of the most earth-shattering mathematical discoveries of all time, which is, if you were to, I would want you, when we're done proving this, to go Google it and see what it says. There's some famous physicists who have said that this was groundbreaking, that this was huge. It allowed them to do stuff with quantum mechanics and string theory and things I have no clue about because I'm teaching high school Calc 2. I am not teaching PhD physics, you know what I mean? But this apparently historically was an incredibly huge discovery. You may have heard of it before. Had anyone heard of this before, that e to the I pi is -1? You might have heard of it, and it's really bizarre because e is transcendental, goes on forever, never repeats. It's not it's weird. Pi is in circles, weird. I is imaginary, right? Super weird. So here we have these two naturally occurring constants that are bizarre, and an imaginary number that poop out actually two of the nicest numbers in the world, because if I were to rewrite this as e to the I pi plus 1 equals 0, I've actually got the two nicest numbers in a relationship. It's kind of like the good girl in a relationship with the devil here. I mean, like, this is bad stuff over there. You know what I mean? We got, well, that was a really bad analogy, but we've got the two nicest numbers in our whole number system, right? Somehow in a relationship with two naturally occurring irrational constants and an imaginary number. That is, for you guys at this level, that seems very strange. Doesn't that seem really, Emma, you're going, that is weird. You might not think it's weird. It is so weird. It's like me saying, Catherine was really a man. What book am I referencing? Come on, famous book, Catherine and Heathcliff. Wuthering Heights. That would blow your mind. If you're like, what? She was a dude? That would blow my mind. This blows my mind. Anyway, here, but we're going to watch it work. Here's what it is. Oh, by the way, if this is you, yeah, what is she about to do? You don't want to know. All right, here we go. This is cool stuff. Here we go. We're going to write E down. Why? Because we know it, and we see it as the base of our very, very strange, earth-shattering new formula over there. E to the x we know is this. 1 plus x plus Julia just said it a long time ago, right, Julia? But when she went ellipsed on me, we're going to keep going. See, I remember things. It's not just a hat rack. I remember you guys told me those were called ellipses. And why did I put that there? Oh, you know what? I'm a little worried that I'm going to forget the proof now based on how the hour's going, but I think I got this. I got you. I got this figured out. How far is she going to go? That's probably good enough. And then I'll do, 4 of them this time. All right, here's what I'm now going to do. I'm going to do IX. All right? So I am going to replace every X with IX. That's legal, right? I'm legal. So I'm going to go 1 plus IX plus, this would be I squared X squared plus I cubed. It's too bad Keith is gone today because he loves when I do this stuff. Proofs that are cool that you don't really need to know, that's when he sits up at attention and stops sleeping. Right, Keith? See, he's going to be listening to this later. So everybody say hi, Keith. They said, what was that? How do you randomly sit in your room? You've got to concretely be, that can't be a random act. That's not randomly sitting. I have a problem. Chilling in his room you can do. You cannot randomly. He will. You know what? You'll have to say you must watch the notes today. Because he might be one who's like, I'm not going to watch them. He would love this conversation. And he would love this proof. So this is ode to Keith right here. I am actually proving this. I think he asked me to record him because he knew this was coming, and he's asked me about this at one time, I believe. Okay, we're done talking about you. Back to our board. I've got to make sure I didn't make mistakes because I was writing while you guys were distracting me. It looks good to me. All right, so now we're going to take a trip back via Wayne's World, back to Algebra 2, because we need to know what these powers of I are. All right, so back to Algebra 2. Don't moan, Algebra 2 is fun. Let's go up here. What is I? Why was it created? What is it? Square root of -1, which doesn't exist, but we're going to make it exist and define, that's the whole imaginary part of it, which makes I squared equal to -1, right? When you square that, it pops out, which makes I cubed what? I squared times I, so -I. Which makes I to the 4th, I squared squared, 1. And it's going to cycle just like 1 to the, or -1 to a power goes 1, -1, 1, -1. I to the powers, this is one full cycle. It goes I, -1, I, 1. The next one's going to be I to the 5th, which is I to the 4th, 1 times I. So it's going to cycle right back to I. All right, and that they cycle in chunks of 4. Are you hip to my jive? All in favor say yo. Okay, so do you need to know the powers of I for your next test? No. Do you need to know this proof? No. Why am I doing it? Because I can, and it's cool, and it's about stuff we just learned. So it's about to get really cool here. Anyway, so I am going to go replace my powers of I with their equivalents up there. So I've got 1 plus IX, and then I've got I squared, so I'm going to be having a minus X squared over 2 factorial, right? What's I cubed according to my Algebra 2 stuff up there? I'm going to replace that with -I. All right. I to the 4th is 1. And I'm carrying this out a ways past our normal ellipses because I want to see more of it. So we're going to keep going a little bit. I to the 5th, according to my calculations, is just I, right? What would I to the 6th be? If it goes I, -1, -1, I, and then it's going to be I what? -1. So I'm going to take it that far and ... Now I'm going to strategically group these. So I'm going to take all my I stuff and write those first because it's legal. So it's addition and that's completely commutable or movable. So I'm going to grab all my I terms and I am going to pull them out front. And then something's going to happen here. That would have been a plus I x to the 5th over 5 factorial, right? What would the next one have been had I continued? Yeah, minus, yeah. So go like that. Go dot, dot, dot. And then I'm going to take my non-I terms and my leash. It's going to let me go. All right, all right. So I got to get close. I got to create the best angle. I have to optimize. Calc AB right there. I got to optimize the distance, which is going to be all about this angle. All right, anyway. Where am I? All right, the non-I terms, which is a 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus that x to the 6 over 6 factorial, which should make the bells in your brain go ding, 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 ding. Right? What's that? Oh. All right. What's this? If I were to factor the I out, ding, 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 I sign. This actually, I sign with my little line. Anyway, I've got I sine plus I cosine plus cosine. That's what e to the ix is. I mean, it has to be based on, I love this proof because it's got the 3 you need to memorize in it. So it's kind of like the vortex of all things you need to know about series and then stuff you don't need to know. So I'm going to replace x. What did Euler do? By the way, this is used a lot in higher levels of math. This even gets a name. They call it, we might need to consult the World Wide Web again. I think it's called sync x. I'm going to write it down and then Ben, you're my internet creeper. Somebody. I think that's what they call it. Not sure. Anyway, I'm going to go replace that with a pi. And I've got I sine pi, right, plus cosine pi. So here we go. Emma, what's sine pi? Okay. What's cosine pi? Oh, oh, that's so cool. There it is. Boom. And you need to consult the web on 2 things for me. I want to know the name for this function. I think it's SINCX. And then there's, and okay. Google this and see what it says. Ah, god dang leash. I'm caught in my, I'm caught in my leash. All right, anyway. Oh, sorry. So, mein Hut ist hässlich. Do you know what that means? You know what it means? What is it? My hat is what? Yes. So that's Euler. Cis. Oh, I had it backwards. Cis x. That is that up there. If you wanted to find cis x, we just did cis pi. Huh, that's cool. Anywho, here's Euler. Here's ist. Do you speak German? Oh. Spreche, mein Hut ist hässlich. It says, my hat is ugly. And then this is e to the I pi plus 1 that I Googled, and it came up with this image that I have no clue, but it looked cool. It's got quantum atom theory, positive symmetry, the future, the... We talked about that yesterday. Was anyone absent yesterday? No? I have to tell her. So I had screenshot him because I always put the pictures of the people by their theorems or their inventions. I try to. But I'd also screenshot a recipe for a lemon pound cake. And I grabbed the lemon pound cake. So on the bottom of theirs it says... That's hilarious. That is really funny and that's so typical. We're done. So your homework is worksheet 5A. Due when? Montag.